Hey guys, this is Mrs. Bird. I'm looking at Unit 5's Lesson 24 project. There's going to be two questions for this part of the project, and I'm going to walk you through how to complete those two questions. So we're still talking about Gartfried and Bernard. We've been talking about those two dragons and how they fly to work throughout the unit. I believe it was in lesson 21 where they said they were flying someplace and they took off and they maintain a flying altitude or height above the ground to be exactly the same. Now they're saying, like, that's not really realistic. They don't actually stay at the exact same height all the time. With every wing beat, their height rises just slightly, and then when they glide, they fall ever so slightly. So just as I kind of picture that, I'm seeing like a beat of a wing might take some, in this case, a dragon, up in the sky. They're going to glide for a little bit, but then they might fall in altitude ever so slightly before another wing beat, then they come up. So I'm almost picturing like this, almost like oscillating up down movement through the sky. It says that this results in motion that for Gottfried is represented by a sine function and then now a cosine function. So this is your introductory to what the two graphs of those functions look like. We're going to be asked to plot points for the graph of Gottfried's motion, which again will be a sine function graph. And then we'll do the same thing with Bernard's. And when you complete this within the tool that the courseware provides, you will be given a code. So make sure that you copy and paste that code correctly into the text box to get full credit. All right, so I'm going to delete this and then jump down to our first question here, where the points in the table on the graph for Gottfried's motion, which correspond to this sine function. So I have 4 times the sine x plus 12. Now we're being asked to plot these points using this tool that, again, the courseware provides. So before I show you how to manipulate that tool that comes within courseware, notice every point has to have an input and an output, or an x and a y. Here is our x, which all of these should start to look familiar to you. These are angle measurements in radians. And then g of x, that's representing the height that Gottfried has. So Gottfried looks like he's starting at 16. Oh, he drops down. Oh, a wing beat, I'm guessing. And then he comes back up, and then he drops down. So I'm already starting to picture what's happening here. But now let's just jump into the tool. I'm going to go to a split screen so that I can see the table, and I'll be able to show you the tool. You can do a split screen too. You just grab whatever window that you want and kind of drag it over until you kind of get that outline. I hope you can see that. And then that's what gives you this split. And then here it just jumped up and you're like, hey, I have all of these other windows open. What do I want on this side? And it's this guy, which is the tool. Okay, so the awesome thing about the split screen is that now I can see the points that I want, and now I can just drag them without having to swap windows and everything around. So point A has an x value of -3/2, and then a y, or an output value, of 16. So we're just going to play the battleship game. There's A, B is -12, blah, blah, blah. C is at -π/2 and 8. D, 12, 0 and 12. It's kind of nice. These are kind of snapping to the points, which is helpful. And then π/2 is at 16. F is at pi and at 12. It's important to make sound effects while you do this. And then give me an 8. All right, there it is. This will be correct when you check your answer. So when you check your answer, it'll give you a code. Just copy and paste that code as you see it exactly into the courseware to get credit. Make sure you use capitals and lowercase. I think it's case sensitive. If you ever make a mistake, like if you put -3/2 at 17 instead of 16, that's something that I would totally do. And you think that they're all correct and it says check your answer, it just tells you to make a mistake. The downside is when you hit try again, it starts you over from square one. So it just doesn't, you would have to replot all of the coordinates again. So just take your time here, plot those coordinates specifically, and you should be good. So that was question number 1. Question number 2 is the exact same thing. I'm going to put A at -3/2 and at 13. B, -1/2, 16. C, -3/2, 13. D, 0, 10. Give me an E, pi/2, 13. Give me an F, 16. Boop, boop, boop. G, 3pi/2 and 13. All right, there you go. So again, check your answer. It'll give you that code. There you go. What the purpose of this is, though, is for you to start to recognize, hey, B of X is a cosine graph. So if I were to play my favorite game of connect the dots, this is what a cosine graph could look like. So something that is oscillating up, falling down out of the sky, in this case, the dragon falling, and then coming back up. Sine and cosine graphs are used a ton in anything that would be oscillating or happening periodically because of that up-down motion. So maybe start thinking about some things that you think could be demonstrated with sine or cosine functions in your life. Bet you there's a lot. We'll also discuss within the next few lessons what this 13 is doing to that graph and what this -3 is doing to the graph. So just a heads up of what to be thinking about, but that is it for this this part of the lesson. So yeah, I'll see you guys soon.